scalability es así, en realidad. Interaction diagram. Yeah. Quedó más o menos bien. ¿Cómo? Tanturi, quedamos para el final, ahí quedamos sobre el pucho. Una foto, quedó más o menos. Soy.
Hello, everyone. Good morning. My name's John, and I'm here to talk about blockchain resource pricing. As soon as my slides advance. OK, so a little bit about me. My name's John Adler. I'm the co-founder of Celestia Labs, and we're building Celestia, a general-purpose data availability layer, and an optimally scalable universal blockchain. There's a lot of buzzwords, and some of them will be explained over the course of this talk. So don't panic too much about these buzzwords yet. I'm also the co-founder of Fuel Labs, and we're building Fuel, and we're leading the R&D on optimistic rollups, and we're also building the most scalable optimistic rollup on Ethereum. Our Fuel v1 optimistic rollup actually launched on mainnet last year, and our upcoming Fuel v2 will be very exciting. Keep your ears posted for announcements on that. Previously, I was at Consensus. I did layer 2 scalability research on things like Plasma, state channels, sidechains, that kind of stuff. And while I was there, I created the optimistic rollup design paradigm. And I did various E2 work and so on. So a bit about Celestia, because I'm here on behalf of Celestia. It's a new layer 1 blockchain. Essentially what it does is it orders data and makes it available. It doesn't actually execute transactions. So it doesn't hold things like the state of applications. It doesn't execute decentralized exchange things. It doesn't have arbitrage opportunities, MEV, and all this stuff. It essentially acts like a decentralized time-stamping server for zeros and ones. And once you have this time-stamping server, any application can build on top of this ordered data. So you can build things like rollups. You can build Cosmos zones or sidechains with shared security. Anything that you can, or individual applications. You can build any one of these things on top of this shared security ordered data. OK, so enough about me and my projects. Let's talk about the meat of this talk, which is blockchain resources, first of all. We'll talk about the pricing part of it shortly. So first of all, what's a blockchain? This seems like it's going to be like blockchain 101, but it's important that we go over things from first principles so that we're all on the same page. So a blockchain is essentially a state machine replication process, or I should say a decentralized blockchain as we use them today is this state machine replication process. There are obviously other blockchains, like Git, for instance, technically a blockchain. That doesn't do state machine replication. But for the way we think about blockchains like Bitcoin and Ethereum, you essentially have a bunch of nodes everywhere in the world, 100, 1,000, 10,000 nodes. And they all independently execute transactions to arrive at the state of some virtual machine. So it looks kind of like this. You have some state at transaction I plus 1 is equal to some function f on the state at transaction I along with transaction I. And what is this f? This f, this function, is the state transition function. And that's essentially describing the virtual machine, if you will, of the blockchain. So in Bitcoin, there's this UTXO thing. In Ethereum, you have the EVM. And essentially, you start with the current state. You apply a transaction, and you get the new state. And then you do this for the next transaction, then the next transaction, and so on. So we agree that if we all agree on an ordering of the transactions, and we all agree that these are the exact same transactions, the exact same zeros and ones, in the exact same order, assuming f is deterministic, we should all arrive at the same state, s. Hence why it's called state machine replication, because all the nodes, they'll replicate the state across themselves. OK. Now this f, it does stuff, right? You do stuff on your computer. It moves electrons around on your chips. It does work. And this work comes in various flavors. And what are these resources that can be consumed while doing this work? So your node could download transaction data, which uses up some network bandwidth, right? In Bitcoin, blocks are 1 to 4 megabytes in size every 10 minutes. So you'd have to download that much amount of data, essentially. So that's network bandwidth. And Ethereum blocks are quite a bit smaller, but they come more frequently. I think they're around 5 to 10 kilobytes, but they might come every 12 to 15 seconds, give or take, depending on the proof of work. So similarly, you just have to download that transaction data so that you can execute it, so that you can get the current state. First, you need the data before you can execute it. In addition to that, full nodes will store transaction data. So once they've downloaded the transactions, once they've executed them, they can just store this data. They can store the zeros and ones. They don't have to read from them again. They just store it on their hard drive. It doesn't require fast latency, random access reads or anything. You can just dump it on a hard drive. You can even dump it on a tape if you wanted to. It'll still work. OK. Now, once you have the transactions, before you store them, I said you have to execute them. So executing them takes up some CPU time, right? If you do an addition, that addition in the virtual machine needs to be executed by your CPU. When you do gas accounting in your VM, it does some subtraction, and then it does a comparison. All of these things are instructions that are executed by your CPU. These are resources, right? It takes electricity. It wears, there's some wear and tear in your CPU. There's real resources being consumed to perform these operations. You also have memory read and write. So let's say you have, I want to copy 1,000 bytes of memory in my VM to another, from one location to another. You probably don't want that to be free, right? You probably want to scale. You want to scale some pricing based on the amount of bytes copied or the amount of data that's being read or written from to memory. Because of course, if you allowed someone to copy 1,000 bytes for free or 10,000 bytes for free, and it would cost the same as 1 byte, then they could just DOS your system essentially. So memory reading and writing is actually finite resources, right? RAM has finite capacity. There's a finite amount of bandwidth, and you want to limit this. There's also storage read and write. So this is from the state, right? Generally, you don't put state in memory. You put it in storage. We'll cover a bit later why this is, especially for Ethereum. And storage, you need to do random access reads and writes into storage. And this is different than history, where it's just like an append-only log, where you just add more history to your, like more transaction data. Storage and state is usually random access. So this one here, you can't put it on a hard drive. You basically have to put it on some sort of SSD, ideally one of those fancy new NVMe SSDs, and not SATA. And especially if you're doing something like an Ethereum full nodes full sync. And this is, of course, much more expensive, right? SSD capacity and bandwidth latency is much more expensive than something like tape, the capacity of some tape, which is extremely cheap. Now, the important thing to note is that these resources that we've just discussed are actually orthogonal, right? Like you could imagine some chain that doesn't execute transactions, which I guess we just talked about in the previous slides. But all it does is just order them. In that case, it wouldn't use much CPU, but it would use potentially exactly the same bandwidth to store transactions and to download them as, say, another blockchain that downloaded exactly the same data but executed transactions. So these resources aren't actually necessarily tightly coupled. They're orthogonal. And this is where things get tricky, and this is why we have this talk on blockchain resource pricing. OK, so in a blockchain system, you need to meter these resources that we just discussed. And you can use this thing that we can just call gas, which is what we name it in Ethereum. But really, it's just some sort of weighting scheme. And the reason you need to meter resources is to prevent denial of service vectors. You don't want someone to create a block that'll take 1 million years to execute. Especially not if you're, say, that in some proof-of-stake BFT system, where you have, a validator just vote on a block. Proof of work is a bit different because, if a block can't be validated in time, it can be orphaned. But let's say in a proof-of-stake system, a block is finalized. If it takes 1 million years to validate, you still have to validate it. You can't just ignore it because your own node was a bit slow. So you need some way of metering these resources to prevent denial of service vectors, so that someone can't create some enormous block. And importantly, once we've metered these resources, we have to put a bound on the resource consumption for each block. And this is this notion of decentralization, the cost to run a full node. OK, so decentralization, let's expand on this. I say it's the cost to run a full node, but what is cost, right? Cost can come in many forms. Obviously, there's the dollar cost, but we're concerned with the resource cost. And the resource cost obviously translates to a dollar cost, so you can denominate them all in dollars. But really, what we're concerned here is this resource cost, because we want to bound the amount of resources someone must spend to run a full node. And that's this notion of decentralization. It's not the number of nodes in the network. It's essentially the cost to run a full node. So all these resources that we discussed before, network, disk capacity, CPU, memory bandwidth and capacity, random access bandwidth and capacity, all of these orthogonal resources, these are parameters that you use to determine the cost to run a full node. OK, so let's start with a not simple, this is actually going to be fairly complex. Let's start with a case study of Bitcoin and how Bitcoin does resource pricing before we dive into Ethereum. Because with Bitcoin, Bitcoin actually has some very interesting history around resource pricing and how some parts of the community don't discuss it as much. The Ethereum community has actually been quite a bit better in discussing resource pricing and adjusting resource pricing in its blockchain. So Bitcoin is a more interesting case study because of how poorly the community has represented this topic. OK, so Bitcoin is a bit different than Ethereum. For its data model, it uses UTXOs. So state elements in Bitcoin are unspent transaction outputs, which you can think kind of like, Satoshi described it as paper bills, essentially. And if you want to spend your paper bill, you have to break it up into change, essentially. Right? You can't spend half a bill. You actually have to break it up. And all the state in Bitcoin is represented as UTXOs. They don't have a notion of accounts. And their execution model is, well, you can spend UTXOs, you can create them, and you can also impose some restrictions on how to spend UTXOs using stateless, i.e. pure predicates. They don't have this kind of rich state that Ethereum has. You can basically define some pure predicate. That's, for example, if you lock some coins behind some hash, then you reveal the script of that hash that happens to be some 2 of 3 multisig, and you provide 2 of 3 signatures from the provided public keys, then OK, you can spend your coin however you want. So it's completely pure. There's no access to state here. It's purely you look at the code, you look at the input data, and that tells you true or false. And if it's not true, then the transaction is invalid. OK, so we'll see this slide a lot because it's the key of the talk. But you need to meter resources, again, to prevent DOS vectors. So how does Bitcoin meter resources first? And second, how does it bound the consumption of the resources in each block? And we need this notion of gas, which might be a bit confusing if all you do is listen to Bitcoin maximalists who talk about block size, because Bitcoin doesn't have a notion of gas, right? It just has bytes, or does it? OK, before we discuss how Bitcoin meters these things, like in the previous slide, we have to discuss this thing called segregated witness, or Segwit, because this is actually the key thing that we're going to use to show how Bitcoin does what it does, and why the developers have made the decisions that they've made. So what's a segregated witness? First of all, this is a classic pre-Segwit Bitcoin transaction, which is technically, you can still broadcast a transaction and have it mined on the Bitcoin network. It still works because Segwit was a soft fork. So transaction looks like this. You have on the left here, you say, OK, I'm spending this transaction from some previous UTXO. Then you provide the signature, or witness data, as it's called more generally. You provide the signature that says, OK, I have the right to spend this UTXO because I'm the owner of this UTXO. Then you tell you tell the transaction where my coins are going, right? So you spend the coin. So you say, okay, I'm spending these coins. I prove I'm the owner of these coins and I have the right to spend them. And then this is where I'm spending them to. This is like the general form of a transaction. And then this just shows how the UTXO model works. That each output here can then be spent in a subsequent transaction, which is again a bit different than Ethereum, which uses an accounts model. Okay, so how does Segwit work now? So in Segwit, instead of attaching the signature data inside the transaction, we just say, OK, the signature data just authorizes the transaction, right? It's some witness that authorizes the transaction. But it doesn't tell us what the transaction does, right? It just authorizes. It doesn't actually tell us anything about the effect of the transaction, right? The transaction will actually spend some coins and generate some coins. That's the effect. The witness data is just witness data. Right? Once you know the transaction has been authorized, you can discard this data. It's completely irrelevant. If I recall correctly, these witness data are essentially committed to in a hash in the Coinbase transaction, which Bitcoin has, something along those lines. So they are committed to in the block. It's just they're not included directly in the transaction and the transaction tree. They're committed to in some other place. But they are very much in the block. OK, now you see that the Segwit transactions, contrary to what some people in the Bitcoin community might say, are actually not smaller than regular transactions, right? They're actually basically the same size. Potentially, they're slightly bigger because you haven't removed the signature data. You haven't removed the witness data. You just moved it from one place to another place, which has a bunch of benefits, which we won't discuss here. But these transactions aren't necessarily smaller. OK, so how does Bitcoin meter its resources? Right? What's the Bitcoin notion of gas? So pre-Segwit, you had one gas or one weight unit per byte. So they would meter things per byte, not per instruction executed like in Ethereum. They would meter it just per byte. And this, to a certain extent, worked. The reason being is that Bitcoin, again, uses these pure predicates. So because of that, it doesn't have to worry about any halting problem or anything. Predicates are guaranteed to terminate. And there's no loops in these predicates. So you just basically go through, scan them in linear time in the worst case. And you always get true or false at the end. You don't have to worry about the halting problem, which is great. So just metering based on bytes isn't completely terrible, right? It gives a good approximation. And if we see down here, how do we bound the resource consumption? Pre-Segwit, Bitcoin bounded the max block size to 1 million of these weight units. So essentially, if you have one weight unit per byte and you have a maximum of 1 million weight units, that's 1 million bytes or 1 megabyte. So that's where the 1 megabyte block size limit comes in. OK, so post-Segwit, what does Bitcoin do? It costs 4 gas or 4 weight units per non-witness byte, which, if you remember from the picture earlier, the non-witness byte tells us what the effect of the transaction is. It tells us it consumes this state, it generates this state, or these UTXOs, right? Because UTXOs are state. And it costs 1 gas or 1 weight unit per witness byte. So witness data has been given this discount. And in the post-Segwit world, the maximum block weight is 4 million. So if you have only witness data in your block, you could have a maximum block size of 4 megabytes, 4 million bytes. If all your data is non-witness data, then your maximum block size is 1 megabyte, of course. And in between, if you have half witness data, half non-witness data, your block size is going to be somewhere between 1 and 4 megabytes. Which is a bit suspicious because we've been told by some people that Bitcoin's block size limit is 1 megabyte, but it's not. It's 4 megabytes, right? The block size has been increased from 1 to 4 megabyte post-Segwit, which seems like it would hurt decentralization. If you remember, decentralization is this cost to run a full node. This seems to increase network bandwidth, right? It seems to increase disk storage. You've now quadrupled the rate at which the history of the chain will increase. And you've quadrupled the network bandwidth required to run a full node. That seems a bit suspicious, right? So why do we choose 4? Not we. Why did the Bitcoin developers choose 4? Why not a million or something, right? And what does 4x discount really mean? So let's pretend in this example we have 4 million weight units, right? Because we're using post-Segwit Bitcoin, and you have an equal number of non-witness and witness bytes. And hopefully my math is right here, but this isn't an equal amount of weight units, right? If you have the same number of bytes of non-witness and witness data in your block, and the block is full, they're not going to have an equal amount of weight units, of course, because witness data has a discount. So you would have 3.2 million weight units of non-witness data and 0.8 million units of witness data, which together should add up to 4 million, right? Because witness data is 4 times cheaper than regular data, or non-witness data. So now let's consider, in this example here, let's say we have some fancy moon math, right? Use some fancy ZK snarks or whatever, and you say, OK, let's make the witness data completely free. It costs nothing for witness data, right? Then you've increased the amount of data you can fit in the, not the total amount of weight, but you can increase the amount of non-witness data in the block from 3.2 million before to 4 million, which gives us only a 25% increase in the throughput of our chain, even though we've done all this hard work to remove this witness data, right? Which is a bit suspicious because we've done all this hard work. We removed this witness data. Witness data takes up half the number of bytes in our block. Why is it only a 25% increase in throughput, right? Previously Bitcoin used to be metered only by bytes. If you remove half the bytes in our block, because again, we have an equal number of non-witness and witness data, you'd expect to have maybe double the throughput. Why is it only 25? Well, it's only 25 because the discount of 4x was chosen, right? If the discount was 1x, in other words, if it was the same cost, then OK, you would in fact double your block size, double your throughput. But because of this 4x, it's only a quarter, so 25%. So it's a bit suspicious, right? There's something fishy going on here compared to how Bitcoin is previously metered and how it is currently metered. So why was a discount chosen? I guess not 4 in particular, but why was a discount given? We'll cover why 4x, I think, in a subsequent slide, but why was a discount given to witness data? And this is going to be very important. So for those of you who are listening at home in a recording or something in a podcast form where you're not actually listening to, you're not actually watching the slides, I'll read out the slides here. And apologies for everyone who's actually here in person. But these are tweets from Peter Woyle, one of the Bitcoin Core developers, explaining on Twitter why a discount for witness data was given. Not 4x, but just why a discount period was given. So the rationale is that, I'm reading the tweets here, the rationale is that witness data can be discounted because it has far lower long-term costs to the network. It does not enter the UTXO set in particular. It is not arbitrarily changing the luggage, charging their luggage differently. It's charging differently for checked and carry-on luggage. John aside, this is a bit of an interesting analogy. So second tweet, Segwit transactions and pre-Segwit transactions that do the same thing are approximately the same size, sometimes slightly less, sometimes slightly more. Segwit discounting rectifies the fact that bytes are not the only metric for measuring network impact. So here he's telling us kind of the intuitions that we built up over the past few slides that just raw bytes themselves aren't exactly necessarily a good way of measuring and metering resources. And he's explaining why in the first slide, which is that witness data, the signature data, doesn't enter the UTXO set. It doesn't enter the state. And if we remember, one of our resources was random access storage on a SSD, because that's where we put the state of our chain. State as in like account balances or the UTXO set. OK, another 2 tweets by the same person. First one, the whole idea of the discount is that block size isn't the best way to measure the cost a block has on the ecosystem. Segwit is a block size increase as it increases the the bandwidth storage costs. Segwit is not a block size increase as it doesn't increase the max UTXO ops per block. Secondly, Segwit changes the metric from size to weight, which I believe, and hopefully the rest of the ecosystem agreed with, is a better way of constraining resource usage. So all of this aligns well with the intuitions we built up over the past few slides, which is that yes, you've increased the block size limit from 1 to 4 megabytes. This does take up more network bandwidth. It does take up more disk storage for history, but it doesn't increase the rate at which the UTXO set grows. Okay, so why did they do this? And the reason is because of what they think, via social consensus and via potentially some experimentation, it depends on what they think the bottleneck is. So from pre-Segwit to Segwit, when the block size will increase from 1 megabyte to 4 megabytes, if the network bandwidth, like if downloading block data, was the bottleneck, would they have done this? The answer is no, obviously. Right? If the network bandwidth was the bottleneck, they wouldn't have increased the cost, the resource consumption of the network bandwidth, right? So the network isn't the bottleneck. Okay, so is the disk capacity, just like to store transaction history, is that the bottleneck? Well, also no, because if this was the bottleneck, well, you probably don't want to quadruple the rate at which history grows. Was the CPU cost a bottleneck, right? Just verifying signatures and performing, and validating the predicates. Was that the bottleneck? Well, also no, because you've potentially quadrupled the amount of signatures you have to verify. So probably your signatures aren't your bottleneck. CPU cost isn't the bottleneck. Is the memory bandwidth, and capacity the bottleneck? Well, Bitcoin doesn't have, complex memory usage and copying bytes and stuff. So no, just by virtue of it being Bitcoin, not because of Segwit. So is this consumption of random access disk bandwidth and capacity, is that the bottleneck? And the answer is yes, right? And as the core dev told us in the previous slides, they want to bound the rate at which state grows, right? That's their bottleneck. And this random access disk capacity, right? That's you put your state on an SSD. You do some random access into the state, and that's what they want to bound. That's the bottleneck. Okay, so some takeaways. What do we learn from Bitcoin and Segwit? Bitcoin's bottleneck is the state growth rate, and this is agreed upon via social coordination. It's not some magic thing that exists because of math. It's not governed by math, right? It's some social construct. Ethereum has similar social coordination stuff. And the agreed upon rate at which the state should grow is 1 million bytes of non-witness data per block. And if we notice, post-Segwit, since the block weight limit is 4 million and each non-witness byte costs 4 weight units, I hope we agree that pre-Segwit and post-Segwit, the maximum amount of non-witness data you can put in a block is unchanged. Right? They've given a discount to witness data, to signatures, but they did not give a discount for regular non-witness data, because those are state-changing bytes essentially. That has remained the same. It's still the same, 1 million bytes of non-witness data per block. So post-Segwit, we haven't actually increased the rate at which state grows. It stays exactly the same, because the state growth is what they've decided is the bottleneck. Right, and you don't want to increase the load on the bottleneck. You can increase the load elsewhere, but you don't want to increase the resource load on the bottleneck, because then you're hurting decentralization. You're making it more expensive to run a full node. So we also note something interesting here, which is that to scale, you have to target the bottleneck, just like how you don't want to target the bottleneck unless you want to hurt decentralization, but also to scale, you need to make resource consumption on the bottleneck more efficient, essentially. You have to reduce it in some way. It could be because you just straight up reduce it. It could be because of increased efficiencies and so on. But specifically, you need to target the bottleneck to achieve scalability. And that's why even if we remove the cost of CPU signature verification of the witness data, you only increase the amount of transaction throughput by 25%, because that isn't the bottleneck. It's only a minor incremental improvement. OK, so Bitcoin does have a concept of gas, contrary to popular belief, and it's this, they call it weight units. And there's no really formal reason for why the discount was given for a parameter 4, right? Having a discount, hopefully we see from previous slides, is a good idea, right? Because it allows us to not increase the load on the bottleneck. But why 4? Why not 8 or 16 or like 1,000? There's actually not a formal reason here. This is like the dirty secret of the blockchain world. Those basically just you run some experiments, you think about it a bit. 4 seems reasonable. It's a good conservative start, but that's about it. They could have chosen 8 or 16. Bitcoin would still work. OK, and another thing to note here, and this is important as we head into the next blockchain, which is that the weight units here need to meter all resources, right? There's like 5 different resource types that we talked about, and these weight units need to meter all of them. Previously, before weight units, it was just bytes, pre-Segwit. Bytes were very inaccurate, right? Because they didn't distinguish between witness data, which doesn't enter the state, and non-witness data, which does affect the state, and which does affect state growth. Right? Bytes were very inaccurate. So OK, weight units are a bit better, but it's still a bit tricky, because if you want to do anything more flexible than what Bitcoin currently has, you now have all the other orthogonal resources other than state usage, right? You have network bandwidth, you have disk storage for history, you have CPU time, you have memory. All of these things are all metered by weight units, right? So this is a bit tricky here. OK, let's look at our next blockchain, or the one we're all here for, Ethereum. How does Ethereum deal with resource pricing? OK, Ethereum uses a different data model than Bitcoin. Hopefully, we're more familiar with this one. It's accounts and storage. Right? You have this big-ass state tree, the Patricia Merkle tree. It has leaves. It has accounts, which have a balance. They have a nonce. And then they can also have contract code. And if they're contracts, they can also have storage. Right? So the storage could be things like token balances for a token contract. And its execution model, rather than pure predicates, it uses some Turing-complete stuff, with obviously some gas limit to prevent infinite loops, and it has this rich storage, right? So contracts can read and write state that isn't explicitly declared in the transaction. In a Bitcoin transaction, in the UTXO world, you have to tell the transaction essentially tells you exactly how the state will be modified. In Ethereum, the state of the chain can be modified arbitrarily during transaction execution, and the transaction body itself tells you nothing. You have to actually run the transaction. OK, so again, we first need to meter resources, and then we need to bound the consumption of these resources for each block. Ethereum has to do this too. All blockchains have to do this. Well, maybe not the centralized scam chains, but you get the idea. OK, so how does Ethereum meter resource consumption? It meters it with gas, obviously. And transactions have a 21,000 base cost. They additionally cost 16 gas per byte for the just data that you put in the transaction. And they cost some variable amount of gas per instruction executed during transaction execution. Now, could transactions, well, OK, before I ask this question, I say we can bound the resource consumption of each block to, I think it's 12.5 million gas per block today. This could increase or decrease in the future. Maybe with once Gasper is here, maybe it'll increase more. I don't know. But I think right now it's about 12.5 million gas per block. OK, so if we transactions have a 21,000 base cost. So every time you send the transaction, you have to pay a minimum of 21,000 gas, even if all the transaction does is send ether from one person to another, right? And it doesn't execute anything else. So if you just remove this cost and said, OK, transactions have a 0 base cost, it costs absolutely nothing to send, would that be a DOS vector? Would that allow someone to create infinitely sized blocks? So show of hands, who thinks this would allow someone to create a huge block with no block size limit? OK, no one's raising their hand. Who doesn't think that? OK, also no one raises their hand. OK, no one knows. That's good. There's actually a trick question. The reason it's a trick question is that I didn't write this here on the slide, but Ethereum simultaneously bounds its block size limit, not just gas consumed per block, but also block size. So you also have to fit, I think the limit is 40 kilobytes. Don't quote me on this. But your block also has to be less than or equal to 12.5 million gas, and less than or equal to, I think it's 40 kilobytes, maybe 4 kilobytes. I don't remember. So there's a 4 there somewhere, and there's some kilobytes. So even if our base cost was completely removed, even if there was 0 base cost, you wouldn't be able to create an infinitely sized block with infinite transactions. You would still be bound by that, that block size limit in bytes. So why is the base cost important? It's actually important at the mempool level. And you want to avoid denial of service attacks at the mempool level. If a transaction didn't have a base cost, people could flood the mempool with what seemed to be completely valid transactions. And all they're doing is sending a simple ether from an empty account to some other random account. And of course, since the base cost is 0, and they're sending, say, 0 ether, then that transaction is perfectly valid. There's nothing wrong with this transaction. So you'd be able to flood the mempool. So this base cost really is a denial of service prevention mechanism for the mempool, because you at least need to have some ether in your account to pay for the base cost at least. So there's it's useful for this thing called standardness rules, which apply not validity in the block, but they apply, you can call them validity, in the mempool. Okay, that was a trick question. Moving on, the accounts. So this gas here accounts for all resource consumption, right? And again, there's 5 different resource types. And accounts for it all with a single unit. What you see when we were looking at Bitcoin, accounting for resource consumption with a single unit is a bit ugly. And because of that, there have been many EIPs to reprice the cost of opcodes and call data and all those stuff. And in fact, just skimming through the core EIPs that have been accepted and implemented, I think about half of them, maybe more, were just about repricing gas. So it's a very tricky thing. But fortunately, the Ethereum community has been very forward and very open in repricing these things to closed DOS vectors and stuff. So it's much more flexible than the Bitcoin community, which took years and years and years to do like a single adjustment in how they meter resource consumption. Okay, so why was 12.5 million gas per block chosen? Why not 20 million? Why not 200 million? Why not 3-second block times? No relation to any chain that is running today. Okay, so why 12.5 million for Ethereum, right? Which, again, our notion of decentralization here, which is the cost to run a full node. So there's 2 reasons why 12.5 million was chosen. The first is the validation rate, which is that Go Ethereum can currently validate about 50 to 100 megagas per second on a regular laptop. I tested this at home. And generally, you want to validate blocks about 50 to 100 times as fast as they're produced, so that when you're doing a full sync, you can catch up in a reasonable amount of time. So you take 100 divided by 100, multiply it by 12-second block times. Whoa, what a coincidence. It's 12.5 million gas per block. Right, so if you increased the gas per block, or you decreased, say, the block time, then you'd be hurting this validation rate. You wouldn't be able to validate blocks as fast, which means that a full sync would take longer and longer and longer. And potentially, if the chain has a huge gas limit, you have a regular laptop, it could take you years to catch up to the head. That's, of course, not very decentralized, right? The second thing is we want to bound the state growth rate. The Ethereum state is currently about 90 gigabytes. Bitcoin state is currently about 4 gigabytes. And the higher the block hash limit, the faster the state growth rate. So we want to bound this to some smaller number, probably smaller than what it currently is, unfortunately. So what are some takeaways for Ethereum? So Ethereum gas has been decent at metering everything except for state growth. Like we saw on the previous slide, Ethereum state is about 90 gigabytes. This is not very good. And this is really the hard bottleneck. The validation rate, we can be a bit flexible for now, but the state growth rate for Ethereum has really been the hard bottleneck. So what are some solutions to this? Because to scale, we need to target the bottleneck. Okay, maybe you can do state rent, right? You can charge people over time for the state they use. You can do state expiry. You can make state just kind of poof, disappear after some time. You can do statelessness, which I think Piper was just talking about 2 talks ago here. Check out his talk if you're interested in the stateless Ethereum stuff that's going on nowadays. You could also do simpler stuff. You could just make storage operations more expensive, which there have been several EIPs to do this. Or you could make call data cheaper. Right? If you make it cheaper, then people are going to use more call data, less storage. OK. Now, what are some challenges in pricing the state? Right? I said, OK, you just make storage ops more expensive. But it's not really that simple. The problem is that storage, you pay for 2 different things. One is you pay for the short-term cost of actually doing a state read or inserting an element into the state. Right? You say, OK, Alice transfers coins to Bob. Bob doesn't have any coins, so let's make Bob a new account, essentially. Right? That's the short-term cost. But you also have to think about the long-term cost of state. Since everything is stored, since the state is stored in a Merkle tree, the more leaves you have in this Merkle tree, the bigger it is, and the more it costs you to go to both store it and to go descend it to get to the leaf. And this is much harder to this doesn't have an immediate impact. Right? It's like you don't immediately see this cost, but it grows over time. So paying for these 2 completely different things with a single unit is very messy. And this is presumably why we've seen so many issues with the Ethereum state size is huge. And when you add statelessness here, you also have to do things like pay for witness data. Because eventually you need to provide witness data to show, OK, I have the state element. So the gas metering also has to account for this, which is a bit tricky, because if you've been following the stateless Ethereum thing, they've been trying to use things like Merkle trees and whatnot, because otherwise witnesses could be very big, and are you paying enough for them, and so on. OK. So let's now cover EVM rollups. Let's take the EVM, go Ethereum, and let's put it into a rollup. And let's see how does this price resources. OK, so a rollup posts data on chain for data availability. It does the execution off chain, and it also all the state growth and stuff that we've been complaining about on Ethereum. All the state growth is moved off chain. Well, that's pretty good, right? But you still need a full node. You still need to run a full node for the rollup in order to verify the rollup is correct and be able to produce new blocks. And you need to run a full node for the main chain, because obviously just running a full node for the rollup is kind of relevant if you don't know the main chain is posting its blocks to is valid. Right? So you need to run two full nodes, which is more than one full node, right? So if you don't do things right, you could actually decrease decentralization of these schemes. And we want to scale, but we want to keep decentralization. If you're willing to give up decentralization, just go use something that shall not be named. So how do these EVM rollups work, right? Similar data model to Ethereum, because you just take the EVM and put it in a rollup, right? Accounts and storage with Turing complete execution. Again, a rollup is not magic. A rollup is a blockchain, and like all decentralized blockchains, you need to meter its resources, and you need to bound the amount of resources used per block. Okay, how does an EVM rollup meter resources? So here's where things get interesting. Unlike Ethereum proper, an EVM rollup has 2 ways of metering resources, 2 ways of metering 2 independent resources, which is good. The first is that you have to pay for the bytes of data availability that you put on Ethereum. And you pay for this on Ethereum. The second thing is the rollup presumably is going to have some limited gas limit, some finite gas limit, and you have to pay to use that, right? So that's a scarce resource. You have to pay to use this. So you have to pay for off-chain computation, and state growth, and all this other stuff, and you can pay this in some form of gas on the rollup. So again, there's 2 different ways of metering and paying for 2 different independent resources. So first is the bytes, the data availability. You just meter it in bytes, and you pay for bytes. And this is great, because you've essentially now paid for a resource exactly in the one resource, and you have 1 unit for that one resource type. This is great. And then this gas accounts for everything else. This isn't worse than we had before. It's presumably a bit better, because you don't now have to also pay for bytes in addition to everything else. So we're getting somewhere. Okay. And you also have to bound the resource consumption of each block. So to bound the resource consumption, we have to say, what's the bottleneck of our EVM rollups? Okay. So we pretend we have some EVM rollup. Why do we choose some gas limit X per rollup block? I haven't said what x is, but we're going to determine the parameter in this slide, but why x? Why not 2x? Why not 20x? Right? Why do we choose this parameter here? Right? Okay, so you have an EVM rollup. It just takes Go Ethereum, puts it in a rollup. Right? Go Ethereum has not changed. It can validate 50 to 100 million megagas per second on a laptop, just like before. We want to validate blocks at the same rate, just like before, because we keep decentralization, right? We don't want to hurt decentralization. So you want to validate blocks 50 to 100 times as fast as they're produced to, again, catch up to the tip of the rollup. So this gives us an X of 12.5 million gas per block, which is the same as Ethereum, right? So rollups don't actually scale Ethereum. Because, again, you've moved execution off-chain, but people still need to run a full node. I mean, sure, you pay for bytes on Ethereum, but you still need to bound the block size limit of the rollup block. Otherwise, you lose decentralization. And similarly, for state growth, well, Ethereum state is currently 90 gigabytes. You probably don't want that on your rollup, too, because that's a problem. That's a mistake. That should never have happened. So to stop your rollup from having such a large state so fast, you probably might want X to be even less than 12.5 million. And maybe you might also want to tweak the gas cost of things like S-store and S-load to be much, much higher, maybe 10 times higher, maybe 100 times higher, so that you don't encounter this state growth bottleneck. Okay. And I want to emphasize here is don't believe everything you see about rollups online. You see posts like this that say, OK, I have an ETH transfer. It takes 12 bytes on a rollup. Therefore, you get 105x scalability by just putting your ETH transfer in an optimistic rollup. That's not all how this works. Right? These kinds of tables only account for the layer 1 bytes. But as we saw in previous slides, we can't just account for that. We need to account for the gas used in the layer 2, in the rollup, so you don't get this 100x scalability. You don't get a 100x cost decrease by just having an EVM optimistic rollup. You can't only account for the layer 1 gas cost of bytes. You also have to account for the actual cost of the gas in the rollup. So some takeaways. You do still need to run a full node for the rollup to be secure and decentralized. You can't avoid this, right? If you're willing to live with fraud proofs or you're willing to trust there's one honest person, don't use a rollup. Use a layer 1 blockchain that makes the same trust assumption and that has a 1 trillion gas limit. It'll be just as secure. Right? If we really want to scale Ethereum and we want to be secure and decentralized and stick to our values that we've been preaching to all these other shitcoins, well, you should probably run a full node you should be able to run a full node for your rollup. Okay. So therefore, a single EVM rollup doesn't provide scalability to the EVM. It can provide scalability potentially to something worse than the EVM. But multiple rollups in parallel could. So it's a form of sharding. Very good. Like this is good. You might lose some composability in sharding, but I mean that's pretty good, right? And it's important that users, and specifically transaction fees, need to pay for both of these things. They need to pay for data availability, and they need to pay for execution. So it's not all bad. It might seem like I'm negative on rollups, but this isn't all bad. Like we separated paying for bytes and paying for everything else, and we pay for bytes with bytes, which is pretty good. We're getting somewhere. So how would we scale with rollups if we want to scale with rollups? Well, I mean, the sharding route that I talked about earlier, which is you run multiple of them in parallel, but you could also do things like have a fundamentally more efficient, fundamentally more scalable virtual machine. And this is what Fuel Labs is building. With Fuel V2, we're building the most scalable optimistic rollup on Ethereum, where we're building Ethereum-style smart contracts. So for the user, this looks just like Ethereum-style smart contracts, but built on top of the UTXO data model, so you can leverage parallelism. Feel free to reach out to me after the talk if you want to know more about this thing. OK, so now let's talk about blockchains as the data layer. We have 12 minutes left. What happens if we have a different blockchain construct that just a blockchain is a data layer. It doesn't execute transactions. It just orders data. This is actually the true realization of Satoshi's vision, TM. And Satoshi in his paper describes, in the Bitcoin design paper, he describes what a blockchain does, which says, we need a way for the payee to know that the previous owner did not sign any earlier transactions. For our purposes, the earliest transaction is the one that counts. And he says here, and this is the important part, the only way to confirm the absence of a transaction is to be aware of all transactions. So what he's describing here is he says, OK, if we have a timestamping server, and if people know all the transactions that ever occurred, they would just take the first valid one and ignore all the subsequent ones. So why is it that we got from here to Bitcoin, where an invalid transaction can't be included in a block. That makes no sense. How do we jump to that? The paradigm of Bitcoin and Ethereum of saying you cannot include an invalid transaction in a block actually doesn't match at all what Satoshi was describing here. What Satoshi was saying here was, if we know all transactions, including the invalid ones, users can just pick the first one and say this is the valid one and ignore the rest. We don't actually need the blockchain to exclude them. Users can. OK, so let's pretend we have a blockchain. All it does is order data, make it available. So what is data model? Well, nothing. Right? It doesn't execute transactions. There's no state. What's its execution model? Again, nothing. And this is what we describe as general purpose, in quotes, which is that the data layer can be used without being encumbered by a very heavy virtual machine that everyone has to validate. All you do is you just look at the data, and it's available, and it's ordered, and it's time-stamped. OK, so again, you have to meter based on resources. You have to bound the consumption of resources. So again, the blockchain, this general purpose data availability blockchain, doesn't execute transactions. All it does is order zeros and ones, bytes, right? So OK, you only have one resource being consumed. It's bytes, right? You download them and you store them, and that's it. Well, that's fantastic, because we know how to meter bytes. You just meter 1 gas per byte, or 1 unit of something per byte, and you're done. And how do we bound the max resource consumption of our block? Well, it's also simple. It's just the maximum size in bytes. Oh, that's so good, right? We don't have to deal with gas. We don't have to tweak the gas costs of individual opcodes and instructions. We just say, it's per byte, and we're done. So the base chain is only used for data availability in this paradigm. And we can meter stuff in bytes, and we can meter bytes in bytes, which is good. And we essentially punt all the state growth, all the execution and everything to layer 2s, 2 rollups, right? Just like how you would do in a rollup on Ethereum today. Right? And they can meter their execution. They can meter their state growth flexibly. It's up to them. They can use some concept of gas. But this base data availability chain doesn't care about this. Right? And you can have separate fee markets and separate ways of pricing these 2 independent resources. Right? Data availability in the base chain and execution on the rollup, or multiple rollups. So let's do a brief case study on ETH2 or Serenity. Post-merge, or I don't know when they changed it from the docking to the merge, but I prefer the docking. Post-merge and post-data only shards, right? Which is the current plan for ETH2. Is this a general purpose data availability chain, like I described in the previous slides? No, it's not. The reason is that to use these data shards in ETH2, you have to fully validate the EVM post-merge. Right? The merge is essentially taking the proof-of-stake consensus and merging in the EVM as it currently is on Ethereum. So if you wanted to use these data shards, you would have to also validate the EVM, which, as we've seen from previous slides, is very heavy because of past mistakes around gas pricing. Right? So this would only really serve as a data availability layer for Ethereum-only applications, for applications that run in the EVM. But we live in a multi-chain world. There are other chains that are running that are innovating outside the EVM, just like how Ethereum is innovating outside of Bitcoin. Right? We shouldn't be maximalist here. And we might not want to fully validate this super heavy EVM to make use of this highly scalable data availability layer. So there is a need for a data availability layer that is general purpose, that is not tied to a heavy virtual machine. OK, now one other interesting thing, this is like segue to a different point. One interesting thing around data availability in particular is we don't actually have to download every single byte to guarantee that a block is available. And this is where things are really interesting. To execute a transaction, you need to fully download all the transaction data and fully execute it. You can't do things partially. For data availability, we actually have a very clever way of not having to download every block. So my co-founder at Celestial Labs, Mustafa Al-Bassam, co-authored a paper with Vitalik Buterin on fraud and data availability proofs a couple years ago. That essentially demonstrates this technique, or he formalized this technique called data availability sampling nowadays. Back then, I think it was called data availability proofs. But there's data availability sampling, which allows you to verify that a block is available without downloading the whole block, which actually means it could be cheaper than 1 byte per byte, or like 1 gas unit per byte for data availability only. And the kind of very naive, or short description here is that the naive way you would try to verify if a block is available is download random chunks from it. This doesn't work because someone could hide a single chunk and then you'd be tricked. So what you do is you use erasure coding. This essentially adds some redundancy. So like say you extend some block to twice its size, and as long as you can recover half of this extended data, then you can recover the whole data. And this kind of error correcting thing has been used in various media encoding things like CD-ROMs and all this other stuff because it's good, right? It means that even if you lose some parts of the data, as long as you have half of the data, you can still recover everything as it was originally. Right? Which is obviously very powerful if your media is subject to scratches and stuff like that. Right? So it's been used for decades. So the intuition here is that every time you sample, you have a 50% chance of being tricked and 50% chance of being right. So if you sample 100 times, then your chance of being tricked is essentially 0, because it's half to the power of n. There's like just speed course. You can find various write-ups and stuff about data availability sampling, but it's key to data availability layers, and this includes sharding. Okay, so what are the takeaways around a general purpose data availability layer? It seems like a good idea, right? It makes gas metering substantially cheaper. It's substantially more flexible than the world computer model, and there is a need for such a system in this multi-chain world. And because of data availability sampling, we can actually verify that data is available without downloading it all, which you can't do if you had execution baked into the base layer. All right, this only works if your chain is like a data availability only chain. Okay, so wrapping up, 2 more slides, just on time. The TLDR resource pricing, all decentralized blockchains have a finite capacity for resources. This is like the notion of decentralization. We all come together and we socially coordinate and say, okay, this blockchain will consume this much resources. It would cost this much to run a full node. So all blockchains need to meter those resources in some way. No exception. Decentralized blockchains. And both data availability and execution must be metered. You can't have a rollup and just only meter the data availability part. You can't do that, right? That's not decentralized. It's not secure. You need to meter both of them. And resource pricing, especially around things like stake growth and these long-term effects that aren't immediately apparent, is actually non-trivial. It's very tricky. It's still a work in progress, and the Ethereum ecosystem has done a good job of exploring and getting close, slowly but surely. It's been a tumultuous, winding path, but they're getting close to having a much better model of how to price execution and stake growth and stuff. So what's the future of blockchain resource pricing, in my opinion? This is the last slide. So if we separate data availability, which again, thanks to data availability sampling, could have some linear cost. And it's much easier to optimize because you're just doing one thing. You separate data availability from execution. And execution happens at layer 2. This is just strictly better than the status quo of doing data availability and execution all on a single layer and all under a single metering scheme. Just separate them. Right, layer 1 provides data availability and ordering and timestamping. Layer 2 provides execution on top of this ordered data through the form of rollups. And the best part of this is you can have separate fee markets for each, right? And you don't have to worry necessarily about having a common metering. You just have separate fee markets. The fee markets will price these resources accordingly. OK, so if you want to contact me, I'm on Twitter at @jadler0. And you can follow my project Celestia at celestia.org. So that's the end of slides. We have 2 minutes left, so maybe questions, maybe not, depending on what the organizers choose.
Thanks, John, for the wonderful talk. Just wondering, what's your take on the state growth of the chains like Binance, Polygon, and whatnot? Yeah, I'm just wondering, they don't seem to care that much about resource metering, right? And I'm just wondering, what's your take on the next months, given the state growth of these EVM-compliant blockchains?
Sure. So for the record, I only know some of these things through secondhand information. But I will say, from what I've heard, a lot of these chains that essentially run Go Ethereum and just dramatically increase the gas limit, it's very hard to run a full node for. So they can choose, and they do choose, to essentially forego decentralization completely and say users can't run a full node on any reasonable end user machine. But in exchange for that, we get massive transaction throughput increase, which they can do, and they will encounter a lot of problems that are in the Go Ethereum codebase because of they're going to have huge state, and the chain will reorg nonstop. I think some of those chains experience like a huge number of reorgs, so they'll just have problems. They can make this choice; it's their choice to make, but they will experience problems.
All right.
Okay, I think that's it for time, but thanks for having me. Oh, there's one more.
Yeah, so thank you so much, John. It was a beautiful talk, and this is Eric Wall here speaking, and I completely agree with the things that you've just said. I just had a minor nitpick on what you said about Bitcoin and whether or not it increases the block size, or whether or not it actually increases the capacity to increase the UTXO set with the Segwit upgrade. And if you move witness data to a separate component, you do fit in more of the stuff in the base block. So if you take out the witness data and you put it in a separate component, which you meter differently, wouldn't that allow you to have more UTXO set updating transactions in the 1 megabyte base block than you would have before? Because in the before Segwit, you had to put all of the witness data in the base block, so it would limit the amount of UTXO set updating transactions in the base block. So don't you think that you could squeeze more UTXO set updating transactions in the base block now after segregated witness? That was just a minor nitpick that with that said, I do think the conclusions that you've come to in this talk are absolutely beautiful, and I really respect the work that you've done on Celestia and Fuel as well. Really seems like a promising rollup.
Thanks for the comment. Your question is actually correct. I hadn't considered that. I hadn't considered that too deeply. I'm not, the biggest. I'm not too deeply involved in Bitcoin, but I think you are correct that moving witness data completely outside that 1 megabyte limit means you could fit more UTXO ops in that 1 megabyte. You are correct, I think, in that. That being said, it's presumably a very small increase, like much smaller than that 4x. But yeah, it would be a minor increase.
Yeah, true.
Thank you.